Penicillins are antibiotics that got their name from the Penicillium mold, from which they were originally extracted. They belong to the pharmacological group of beta-lactam antibiotics. What all beta-lactams have in common is a beta-lactam ring in their structure, which gives them their name, and also the mechanism of action, the inhibition of cell wall synthesis in bacteria. So our body consists of multiple eukaryotic cells, while bacteria are prokaryotic, meaning they're primitive, single-cellular organisms. Most have a slimy capsule made out of polysaccharides and a cell wall which encapsulates and protects the bacteria like a suit of armor, and offers structural support. Bacterial cell walls are made of a substance called peptidoglycan, or murein. Peptidoglycan is a molecule composed of long strands of amino polysaccharides running in parallel. These are made of segments of N-acetylglucosamine, or NAG, and N-acetylmuramic acid, or NAM, in an alternating pattern, so NAG, NAM, NAG, NAM, and so on, like a pearl necklace. At the tips of and protruding from the NAM subunits are tetrapeptide and pentapeptide chains. These peptide chains can link to other peptide chains from the neighboring strands through a process known as transpeptidation. This is carried out by an enzyme called DD transpeptidase, or penicillin binding proteins, or PBPs. Now, these enzymes are like locks, and there are specific binding areas for the pentapeptide keys to fit into. Once the key goes in the lock, the PBP enzymes fuse them together, creating a stable link between the two amino polysaccharide strands, and strengthening the cell wall. In essence, all beta-lactam antibiotics, like the penicillins, somewhat resemble the tetrapeptide chains. Inside the bacteria, PBP enzymes will mistakenly bind to the beta-lactam antibiotic molecule, instead of a tetrapeptide, and stick inside the PBP forever. Like putting chewing gum in a keyhole, permanently disabling it. As more and more PBPs get disabled, the cross-linking fails to happen, and the wall becomes weak and unstable. If the affected bacteria attempts to divide, their cell wall will collapse, killing them in the process. Now, some bacteria have developed resistance to beta-lactam antibiotics. The most notable is the notorious Staphylococcus aureus, which evolved to have enzymes called beta-lactamases or penicillinases that break down the beta-lactam ring within the antibiotic, rendering it ineffective. In response, though, we started adding beta-lactamase inhibitors, like clavulanic acid, that would bind to beta-lactamases and inactivate them, again like the gum into a keyhole. Another approach was to create new kinds of beta-lactam antibiotics, like methicillin, which has a large side chain that wouldn't fit into the keyhole of the beta-lactamase. These did work pretty well, until some Staphylococcus aureus developed PBP site mutations that changed the shape of the keyhole. So even if beta-lactamase enzymes can't break down these antibiotics, they won't fit into the PBP enzyme and thus won't work. We call these bacteria methicillin-resistant Staphylococcus aureus, or MRSA. This poses a huge problem, because it makes MRSA virtually untreatable by beta-lactam antibiotics. To treat MRSA, we resort to so-called reserve antibiotics belonging to the glycopeptide antibiotics, like vancomycin and teicoplanin. But even that might come to an end, as MRSA is also developing vancomycin resistance, becoming VRSA. Now, going back to penicillins, we can divide these medications into three main groups based on their spectrum of activity, which is how many species of bacteria they can effectively treat, and how vulnerable they are to beta-lactamases. Examples of narrow-spectrum penicillins that are susceptible to penicillinase are penicillin G, applied intramuscularly, and penicillin V, applied perorally. These are the classics, still pretty usable against common gram-positive bacteria like Streptococcus pyogenes, that causes pharyngitis, and gram-negative bacteria like Neisseria meningitidis, that causes, bacterial meningitis. They're also effective against spirochetes, like Treponema pallidum, that causes syphilis, or Borrelia burgdorferi, that causes Lyme disease. However, they do not work well against a lot of gram-negative aerobes. And some of the bacteria they used to treat well back in the day, like Staphylococcus aureus, strains of Streptococcus pneumoniae, and recently Neisseria gonorrhoeae, have developed resistance. Now, we want to make a simple and fun mnemonic that'll help you efficiently memorize and retain all these crazy farm facts. So imagine a street that's wide at one end and very narrow at the other. We'll put our narrow spectrum drugs right in the middle of the street, which is kind of narrow. This group of drugs will be represented by an artistic panda, holding a giant pen which represents penicillin. His drawing will represent the bugs that this class of medication treats, which includes a large pie at the bottom for Streptococcus pyogenes. Popping up in the middle of the pie is the Loch Ness Monster, or Nessie, for Neisseria meningitidis. Next, there's a parakeet sitting on Nessie's head for the spirochetes. Since we put something on Nessie's head, it helps you remember that it's Neisseria meningitidis, and not Neisseria gonorrhoeae. Alright, so moving on. Broad-spectrum beta-lactamase susceptible medication, like amoxicillin and ampicillin, are characterized by their wider spectrum of activity when compared to, say, penicillin G. They're effective against a wider variety of gram-negative bacteria, like Haemophilus influenzae and Moraxella catarrhalis, which cause respiratory infections and pneumonia, Helicobacter pylori that causes peptic ulcers, as well as Salmonella, Shigella, and Listeria species that cause diarrhea. Listeria in particular is very dangerous to babies and pregnant women, and can lead to meningitis. This class is characterized as pregnancy category B, meaning no risks have been found for use during pregnancy. Amoxicillin in particular is the antibiotic of choice in pregnant women. These medications can also treat the same gram-positive bacteria treated by penicillin, but they're less potent. Other members of this group, sometimes called extended-spectrum penicillins, include piperacillin and ticarcillin. These have even more gram-negative coverage. Most notably, they're effective against Pseudomonas aeruginosa, a bacteria so hardcore and resilient, it swims laps in hand disinfectant just to wake up in the morning. That's why these are sometimes called anti-pseudomonal penicillins. Broad-spectrum penicillins are still quite susceptible to beta-lactamases, but can work really well if combined with a beta-lactamase inhibitor, like clavulanic acid. Alright, so back to the mnemonic. Let's go to the widest part of the street for the broad-spectrum penicillins, which will be placed on a tree. For the drugs, let's put a mockingbird for amoxicillin, and a magpie for ampicillin. The mockingbird is singing a lullaby to a baby, so it's safe for pregnancy. These birds are about to enjoy a meal which represents the GI bugs. This includes salmon for Salmonella, and shellfish for Shigella. Let's also add in a bottle of Pepto-Bismol for after the meal to help you remember Helicobacter pylori, and a bottle of Listerine mouthwash to help you remember Listeria. Higher up in the branches are the respiratory bugs. There's a family of vampire bats for Haemophilus, since hemo means blood and philus means like. Then there's an oversized axe embedded in the tree branch which represents Moraxella, more axe. At the bottom of the tree, which is wider than the top, let's put in our extended spectrum medications. So we have a tiger for ticarcillin, and he's brought a large pepper shaker with him for piperacillin. Remember that these medications can treat all of the bacteria higher up in the tree. The tiger is also hunting for his favorite meal, which is a guy wearing a Mona Lisa mask representing Pseudomonas. Next are the very narrow spectrum beta-lactamase resistant medication, which are also called anti-staphylococcal penicillins, and they were created to fight bacteria like Staphylococcus aureus and Staphylococcus epidermidis that often had the beta-lactamase enzyme. These medications have a large side chain that prevents them from fitting into the beta-lactamase enzyme, so they can't be broken down. Now, these medications include methicillin, the first medication of this type, oxacillin, nafcillin, cloxacillin, and dicloxacillin. They did work quite well, until some Staphylococcus aureus developed the PBP site mutations and became MRSA. Alright, so back to the mnemonic. Now we'll go to the very narrow end of the street for the very narrow spectrum penicillins. There's an ox for oxacillin carrying a napping fox for nafcillin on his back. The fox fell asleep trying to learn from a math textbook that's too hard, methicillin. He sets a regular and a digital alarm clock, cloxacillin and dicloxacillin, on the horns of the ox to help him wake up. To remember what this class of medication treats, let's have the ox going down to the river to find gold, representing Staphylococcus aureus, and animal pelts for Staphylococcus epidermidis, since epidermis means skin. Penicillins are generally a safe and well-tolerated family of medications. However, they do sometimes show unintended adverse reactions, like gastrointestinal upset, diarrhea, or taste disturbance. Most important of these is allergy to penicillin, which shows up as urticaria, which is a red, raised skin rash, with severe pruritus, or itching. This can progress to fever, joint pains, hemolytic anemia, kidney failure, and anaphylactic shock. Around 5 to 10% of patients will manifest a reaction ranging from mild to severe, or even life-threatening with repeated use. Since the penicillins are very structurally similar to each other and other beta-lactam antibiotic like cephalosporins, they could be cross-reactive, meaning if somebody was given, for example, penicillin G in childhood, they can develop an allergic reaction to amoxicillin or cefazolin. Other adverse reactions are not specific for penicillins, but are still fairly common with antibiotics. One such example involves superinfections by more resilient organisms. Usage of antibiotics will also obliterate our native flora, making us susceptible to, say, yeast infections, like candidiasis. The death of the bacteria itself can also cause problems. When large numbers of bacteria die off simultaneously, parts of their cell can remain in the body and trigger our immune system. One such example is Jarisch-Herxheimer reaction, which might happen after initial treatment of syphilis with a beta-lactam antibiotic. Individuals can develop fevers, chills, muscle pain, and flushing for a few hours after administration. Alright, as a quick recap, we have a street with a wide end and a narrow end. At the wide end is the tree representing our broad spectrum penicillins, like amoxicillin and ampicillin. Don't forget about the extended spectrum penicillins like ticarcillin and piperacillin at the bottom of the tree. Next, in the middle of the street, which is kind of narrow, is the artist Penda holding a giant pen for penicillin. At the narrowest part of the street is the ox with the fox on its back with the math book and the clocks on his horns, which represents the very narrow spectrum penicillins like oxacillin, nafcillin, methicillin, cloxacillin, and dicloxacillin. But wait, there's more. Here's a mind map with all of the mnemonics from the video. Go ahead and pause the video so you can test yourself to see what you remember. Stay tuned for the answers at the end.